So, good evening, everyone. Thank you. I'm Brian Green, co-founder of the World Science Festival with Tracy Day, and this is the fourth day of the 2013 festival. And I'm pleased to say that all of the programs have sold out, which is a great sign, I think, for humanity. Do want to remind you, in case you don't know, I think many of you do, that tomorrow is the Ultimate Science Street Fair. That will take place right out there in Washington Square Park. There are a variety of things for kids and adults, so you should come. It will be a great time. In terms of the festival itself, it's perhaps worth noting that in the last 5 years, with this now going to the sixth, festival has reached over 850,000 live audience members. We've brought over 700 top scientists to speak on a whole range of subjects. Millions of more people have watched the programs online, and none of this at all would be possible without the generous support of our sponsors. So I just want to quickly thank them: the Simons Foundation, the Sloan Foundation, John Templeton Foundation, and also our major sponsors, ANZIF, Con Edison, and the Kavli Prize. Please join me in thanking them. I also want to mention that although the festival proper ends on Sunday, June 2nd, we are transitioning. The World Science Festival is transitioning its website from what has long since been a ticket selling site that you all are familiar with to a science destination where programs that you may have wanted to go to but couldn't get tickets for or were happening at the same time as another program, you'll be able to see those programs, excerpts of those programs, various web content that is being designed just for the World Science Festival website. So you should go there. Check it out. There'll be activity there now all year long. Okay, for tonight's program, I just want to say a couple words about it. It is a powerful panel talking about a polarizing subject that is led by, in the discussion, by one of the world's great journalist moderators, John Hockenberry. So it's really going to be a treat. I perhaps should say just a couple of words. I have spent some time writing about and lecturing about this subject, and there are going to be a lot of views, strong views, that are going to be voiced here tonight. We had to have security called in, backstage before, but I think everybody's sort of calmed down for the time being. Maybe sort of Jerry Springer-like conversation going out here, but so here's just a couple of thoughts just to set the stage. So first off, when one talks about the multiverse, there's not one idea of multiverse. There are many ways in which the multiverse has come up in physics, many flavors of multiverse. I'm not sure exactly what's going to be covered here tonight, but it's good to keep in mind that various arguments, various perspectives from a whole different variety of vantage points have led us to at least consider this possibility. The second point is one that, of course, is quite general in the world. Whenever there are strong opinions and there is a kind of debate-like atmosphere, people tend to go to the extreme version of their perspective in order to give the strongest argument to combat whoever is attacking them. The truth, of course, in many of those situations lies somewhere in between the two extremes. So my view, which is the right view, is that anybody who says that the idea of other universes, the multiverse, anybody who says that that idea is absolutely nuts is really being extreme. There are reasons for taking this idea seriously, and you'll hear some of those reasons here tonight. Anybody who says that the idea of a multiverse is absolutely right is also being extreme, kind of hyping the idea, because there isn't really any foolproof evidence by any means, not even close, that the multiverse is definitely the correct description of reality. So somewhere in between those two extremes is the right answer, but certainly it is a subject that is exciting and worthy of attention, and the discussion here tonight, I think, will make that very clear. So, without further ado, please enjoy the program on the multiverse.
It's 8 o'clock. Do you know where your universe is? Start by imagining a tropical lagoon. To the fish that live here, this watery world is all there is. This lagoon is their entire universe. They have no idea there's anything beyond. Well, they are fish. And that theirs is actually just one of a huge number of bodies of water on Earth's surface. Some like theirs, and some very different. So now that you are a fish, what if you got a clue that this world of ours is just a tiny lagoon in something much bigger? Could your fish brain handle that? We humans always assumed our universe is one of a kind, unique. Even the word universe reflects this. We think that one and only universe came into existence nearly 14 billion years ago with what's called the Big Bang. In the 1980s, a group of young physicists, including Andre Linde, Paul Steinhardt, Andreas Albrecht, and Alan Guth, came up with an enhanced version of the Big Bang theory. They proposed that in the first instant after the Big Bang, the universe underwent a burst of incredibly rapid expansion called inflation. And satellite measurements of the heat left over from the Big Bang now support the idea. But surprisingly, the theory of inflation also suggested something very odd. According to inflation, the Big Bang that created our universe may not have been a one-time event. Instead, it could have happened again, and again, and again, an infinite number of times. And just as our Big Bang created our universe, each of those Big Bangs would have created other universes, a process that would continue eternally. So Guth, Linde, and others concluded that instead of a universe, we might be living in a multiverse. The math shows, it's always the math, right, that the multiverse would contain a huge variety of universes, ranging from some that are nothing like ours to others with duplicates of Earth and each and every one of us. In fact, the existence of so many other universes would mean everything that can happen will happen in one universe or another. It's an intriguing, out-of-the-pond idea, but also controversial, igniting a fierce debate in the scientific community. Several scientists, including some who helped create the theory of inflation, have come up with counter-arguments to the multiverse. A theory that predicts everything predicts nothing, one wrote. And critics object that considering the multiverse is more akin to philosophy than science. So who is right about the multiverse? We all know how our fishtail would turn out if those fish could find a way to see beyond their lagoon. They would discover that their universe is not unique, and that Earth's surface is covered with lagoons, ponds, lakes, seas, and oceans teeming with all kinds of creatures. This discovery would forever change their picture of reality. But what about us? What would it mean to find we're part of a much larger multiverse? How seriously should we take this idea? And what if I just zapped out of this 2D multiverse and appeared before you right now?
Evidence of a multiple universe you might find on this stage tonight. We're going to talk about some pretty esoteric and wonderful stuff. Welcome to the World Science Festival Multiverse Big Idea, or Brian tried to kind of warn us, didn't he, that this could get pretty heated. So maybe I should just completely change my introduction and think maybe just to get us all ready. Welcome to 2013 WrestleMania Cosmology. Are you ready to rumble? Something like that. I mean, that is why you bought tickets, right? But seriously, is the multiverse idea something that's implied by deficiencies in existing cosmological theories? Or is it something some scientists need to help them explain certain unresolvable problems in existing theory? Basically, we are dumped down here in the middle of the incompleteness of cosmology right now, and our mission is to move from stuff we know to stuff we really don't know, and to take you all along on this journey. But let me just say that in a parallel universe where the Knicks are still in the playoffs, where President Romney closed Gitmo, where David Petraeus did not have an affair, and Margaret Thatcher is still Prime Minister of Britain, yes, it would be a very different world than we see today. Are all probabilities possible, and do they exist simultaneously in multiple universes? Well, I guess if that was the case, there would be no Las Vegas, right? They need it to turn out one way and not the other. We have an extraordinary group of individuals to talk about all of this from the standpoint of very particular positions that will be argued here on this stage, and also from the standpoint of teaching you how this argument is actually playing out with as much of the real physics as we can provide to you all. I'm going to just sit back and let them talk. Please welcome onto our stage André Linde. Studied physics at the Moscow State University. In 1975, he started his work at the Lebedev Physical Institute. In 1985, he became a professor of physics. In 1989, he joined the theory division at CERN, Switzerland, and in 1990, he became a professor of physics at Stanford University. Also, please welcome Alan Guth. Professor of physics at MIT, world-renowned for his discovery of inflationary cosmology, the dominant cosmological paradigm for over 2 decades. His current research focuses on developing mathematical tools for quantitatively analyzing inflation's suggestion that there are an infinite number of universes. And now, Andreas Albrecht. The discovery of cosmic acceleration has been transformative to the field of cosmology. Albrecht is known for his groundbreaking work on dark energy theory and phenomenology. Albrecht moved from a professorship at Imperial College in London to UC Davis in 1998 to build the cosmology program there. He's now physics department chair at UC Davis and is a fellow of both the American Physical Society and the Institute of Physics. And finally, Neil Turok. After his PhD at Imperial College in London, Turok was associate scientist at Fermilab, professor of physics at Princeton, chair of mathematical physics in Cambridge. He's now director and Niels Bohr chair at the Perimeter Institute for Theoretical Physics in Ontario, Canada. Please, an applause for all of our panelists. I love that name first and then welcome you on. It does have a kind of a WrestleMania feel to it. I think that's let's start with you, Neil. We begin with what we know. The Big Bang is something that was controversial when I was growing up in the 60s, but is something that's a fairly settled question right now.
It is for most of us, and maybe the way to begin this evening is by emphasizing that the four of us agree on far more than we disagree on, in fact. Of course, what we're always interested in are the questions on the frontier of what we know. But over the last 3 decades, we have learned an amazing amount about the universe, and the vast majority of that we can all agree on. If I could show you a picture of this. Is it coming?
It'll be there in a moment, yes.
Okay.
This is a picture of the Big Bang or a picture of agreement among physicists?
Same thing.
There we go.
So yes, we have learned to believe in the Big Bang from many lines of evidence. We are fairly confident that around 14 billion years ago, the universe started out in what I call a ball of light. a very intensely hot piece of energy and radiation about 1 millimeter across, which was expanding with enormous speed. And its space was expanding, it wasn't a bang. In fact, the name is a misnomer. It's big expansion. And you have this tiny object which literally expanded into everything we see today. And so the fundamental, here it is on the left, the ball of light expanded, this radiation filling it cooled. Out of that emerged the particles clumping together to make atomic nuclei. Then those nuclei clumped together with electrons to make atoms. And the atoms clumped together to form galaxies and stars and planets and all the things we see today. And so the big mystery in cosmology is what banged, what actually created the ball of light. The second mystery, which has become highlighted recently, is what's going to happen in the future. And here the story is equally mysterious, is that space is not empty. The space between galaxies is not empty. We know it's full of energy, which we call the dark energy. And this has an effect of causing the expansion to accelerate. And so we see the universe now accelerating its expansion, emptying out. The future looks to be very dark, cold, and isolated. So this is
Really? That's great to hear.
Yeah. So we have this picture of the universe with tons of data reinforcing it and some very fundamental mysteries. One of the most interesting is that that little ball of light wasn't completely smooth. It was almost perfectly smooth, but had variations in the density of matter from place to place across it at a level of about 1 part in 100,000. And the question is, where did those variations come from? They're incredibly important because those variations later clumped into galaxies and stars and planets. So they were our ancestors. And if you see in the picture at the top, the Planck satellite, just in the last couple of months, released its maps showing us a picture of what those variations looked like just when the radiation from the hot plasma of the early universe was released to us about 400,000 years ago. So we are seeing, we believe, the ripples on that tiny ball of light as the universe around us came into existence. On the other side, we've learned a lot about the vacuum. Just last year, we learned that it's full of the Higgs field, that space is not empty, not just because of the dark energy that fills it, but it's also full of this Higgs field which controls the masses of the particles we are made of. And so we've learned this vacuum is very intriguing. This is all about one universe. I haven't mentioned multiple universe. And initially, I was hoping this format would be much more of a debate, and I hope it will be, because trying to explain this has encouraged theorists to build models. And literally, the last 30 years have been an extravaganza of theoretical models. And the multiverse is certainly in our minds, okay? Whether it's in reality is, for me, a very open question. What I would say is that the evidence from last year, from the Large Hadron Collider in discovering the Higgs boson, goes strongly against the multiverse. Instead, most theorists were expecting more than one Higgs bosons, lots of other particles, lots of complications. Instead, the Large Hadron Collider found just one Higgs boson with amazingly simple properties. Properties which indicate that perhaps we can trace what happened to the Higgs field all the way back to the singularity itself. And they point to extraordinary simplicity in that singularity. Likewise, the Planck satellite is showing us a far simpler pattern than the inflationary models in general were predicting. Inflation isn't really a theory. It's a vast collection of models, and the vast majority of those models have been ruled out by the data. So I would say the universe is giving us a glimpse of extraordinary simplicity and beauty in its structure. What we need now are theories, principles, mathematics, which explains the simplicity we see. The multiverse is all going in the wrong direction. It's a bunch of...
All right, let's hold on for 1 second. You said, let me just ask you a question, and we will get to the other corners here in a moment. You said that the Planck satellite gives us a picture of something that happened 400,000 years ago?
We can see it as it was 400,000 years ago.
400,000 seems like a blink.
Whoa.
Seems like a blink of time, 400,000. Just
earlier than that...
Not a go.
Yeah, you
Since
said
the
it
Bang.
wrong.
Sorry?
It's not 400,000 years ago. It's
Sorry.
since the Bang.
Sorry.
I sensed the
Since the
fact
Bang.
error. Yes, I sensed the fact. So I just wanted to clarify.
30, sorry. Since the Bang.
Since the Bang.
Bang.
Because if the
it's
Big
on the
Bang only
picture.
happened 400,000 years ago, that would be a
Sorry.
big news story.
Yeah,
I would be covering that.
We converted
Since
it
the Bang.
in the
Yeah. Okay. All right.
Since the Bang. Sorry.
You anticipated the next segment of our program, and that is inflation theory, which while perhaps less generally accepted than the Big Bang, is also embraced by a lot of scientists who are concerned about how the look of the universe that we see now is not explained solely by a Big Bang that expanded continuously. There would have to be a period of time of rapid inflation where all of the matter in the universe was together to explain the uniformity that we see today. Here to help us understand that, Alan Guth.
Thank you. To describe how inflation fits into the Big Bang picture that we've already talked about a little bit, I think the key word is a word that comes from Hollywood, the word prequel. Inflation is a prequel to the conventional Big Bang picture. Can we have the next slide here? Because it shows the timeline. There's inflation way on the left, top left, cosmic inflation at about 10 to the minus 30 seconds. It provides a story that precedes the expansion of the universe, the formation of galaxies, et cetera, et cetera. And basically, where it fills in is an important point which Neil actually mentioned. The Big Bang theory is a misnomer. What we call the Big Bang theory scientifically really says nothing whatever about what banged, why it banged, or what happened before it banged. It really says nothing about the bang. It's a story. The classic Big Bang theory is the story of the aftermath of a bang. It describes what happens after the matter was already uniformly expanding with the space along with it.
You use more technical terms. You don't say pre-bang, post-bang, stuff like that.
Not more technically. You're right.
Slightly,
In a technical
okay.
sense, we've
Yeah.
done that. So it goes over well with
Please continue, yes.
Yeah, I tried it. Okay, so the way in which inflation explains the bang is in terms of a very surprising feature of physics, I think very surprising to most of us, which is the fact that gravity can actually sometimes act repulsively. Now, those of us who learned about gravity in high school and learned Newton's law of gravity probably think this sounds crazy, because Newton's law of gravity is purely an attractive law of gravity. But that got changed with the advent of Einstein's theory of gravity, which is the theory called general relativity. According to general relativity, gravity normally acts attractively, but there are circumstances under which it can act repulsively. And furthermore, modern particle physics very strongly indicates that at very high energies we expect there to exist the kind of states of matter that would produce the repulsive form of gravity that general relativity allows. And inflation is basically the proposal that the bang of the Big Bang, the driving force behind the expansion, was this repulsive gravity as allowed by general relativity.
And can I just ask you, so the math of both the Big Bang and the way sort of Einstein presents how the universe works suggests that at high energy states, the gravity that we understand becomes an explosive force pushing outward rather than pulling inward.
That's right. That is right.
And so the question is, you go about trying to test how that would actually work in the time span of the immediate aftermath of the Big Bang.
That's right. That's right.
Please continue. I just want to make sure I was on the same page. This is always very terrifying for me Okay.
Okay, good, good. Okay, I should add that the inflationary model depends heavily on another very peculiar property of physics, a property that I think most of us are not used to, which is the idea that energies can be either positive or negative. And in fact, the total energy of our universe is completely consistent with adding up to zero. Zero in a form where all of the positive energies are in the form of matter and radiation, all the stars and galaxies. As you probably know, mass is really just a form of energy according to relativity, with the famous E equals mc squared equivalence. Any mass is equivalent to an energy, which is the mass times c squared. All of those are positive contributions to the energy. The negative contribution comes from the gravitational field that fills the universe. Gravitational fields actually have a negative contribution to the total energy. And as far as we can tell, the total energy of the universe is consistent with being exactly zero, with the cancellation of these positive and negative contributions. And that's very important, especially to this idea of a multiverse, because it means that you can produce universes for free. It costs nothing to produce a universe. The universe is, in some sense, the phrase I like to use is that's the ultimate free lunch. Now,
I actually really was impressed by the universe until you just said that.
that is right.
I'm sort of yawning as another universe.
Yeah, no, what I really am saying is that the universe is a gigantic big nothing as far as quantities that we think are conserved, quantities that cannot be either made or destroyed. So universes can be made for free, as far as we can tell.
So the conditions that establish the Big Bang and produce one universe are equivalent to a Big Bang which produces infinite universes, based on the math that you've explored.
Equivalent is maybe a little too strong a word. I'll bet Neil will object to it.
Yeah.
But the same mechanisms, we believe, those of us who believe in inflation, that produce one universe can produce many. And as far as I'm concerned, that's the norm in science. I think there's nothing that we know that can only be produced once. So I think this just proves that cosmology can be like other sciences. Now let me finish by describing some of the things that this inflationary model can explain. Once you decide that this mechanism of propulsion is very likely the way our universe was born, you can ask what kind of universe does it predict and does it agree with what we see? And in fact, it allows us to understand three very important properties of our universe. One is it allows us to understand the uniformity of our universe. As I think was already mentioned, this cosmic background radiation that has been now measured with incredible precision has fluctuations which are incredibly interesting, and we'll be talking about them tonight. But these fluctuations are incredibly tiny. They're only at the level of 1 part in 100,000. To an accuracy of 1 part in 100,000, the cosmic background radiation that we see is the same intensity in every direction that we look. The universe is just unbelievably uniform on large scales. And that cannot be understood in the conventional Big Bang picture. But inflation explains it very naturally. You start with a very small universe, which becomes uniform before inflation, and then inflation just takes over and magnifies this tiny uniform speck to become large enough to include everything that we observe.
So the moment the inflationary period ended, we were together enough to have produced the uniformity that we see today, and that post-inflation period, everything kind of got disconnected and clumpy and all of that, but the conditions for uniformity were already set in the inflation period.
Absolutely, right. That's the picture.
Doing all right. Doing all right.
Now, a second very important prediction that this inflationary model makes is for the overall mass density of the universe, the total amount of matter per cubic meter that we see. When inflation was first proposed, the prediction differed from what was observed by about a factor of 3, and a lot of times my astrophysicist, astronomer friends told me that inflation was obviously wrong, that it predicted the wrong mass density. Now it's right on. The observations have changed. The main addition is this dark energy. When you add in the dark energy, the prediction of inflation is right on the dot, now measured to an accuracy of about 0.5%, and in complete agreement with what inflation predicts. And finally, and this will be talked about more later, I'm sure, inflation makes predictions for these non-uniformities that we observe in the cosmic background radiation and in the matter distribution in the universe as a whole. Inflation predicts it because in the context of these inflationary models, these non-uniformities actually arise due to just purely quantum uncertainties. Classically, inflation would produce an absolutely smooth universe, but because of quantum uncertainties, the mass density is a little bit higher in some places and a little bit lower in other places, and inflation predicts what we call the spectrum of these non-uniformities. That is, it predicts how the intensities vary with the wavelength of the non-uniformities. And the measurements show that the predictions of inflation are, again, essentially right on the dot. Marvelous agreement between the prediction of the simplest models and what is actually observed. So I'll stop there.
Let me ask you one question as a matter of clarification, and then we'll move on to some of the experimental evidence for some of this. Many of us here in this room who are familiar with Star Trek and sci-fi videos of one kind or another, who've seen the Big Bang in person, as I have, understand it to have gone from a very small point, but continuously to have expanded. The inflationary model suggests that there was a rapid period, then a really rapid period, and then a slow period. And I've heard that likened to what happens when a marble rolls down the side of a very steep incline. It goes from a flat state up here to a flat state down here, but as it's rolling down, it's moving very, very, very quickly. How do you understand that it's possible for something very discontinuous to have happened in what we think of as a continuous expansion of the universe?
Okay. Yeah, the cause, well, first of all, it's a little more continuous than you think. That is, inflation doesn't really speed up the expansion of the universe. It really just stops it from slowing down as fast as it would have otherwise, at least in most models. It depends a little bit on what assumptions you want to make about what happened before, where things are very uncertain. At the end, inflation turns off. It turns off because these peculiar materials that create the repulsive form of gravity are fundamentally unstable. So they decay like radioactive substances decay. And when they do, the universe doesn't suddenly slow down. What turns off is the acceleration. The universe continues to coast at a speed that's initially set by the speed of expansion at the end of inflation.
All right, so let's move to the question of experimental evidence of all of this. All of these gentlemen have something to add to that discussion. But Andres, let's begin with you.
Well,
the Planck satellite's been referred to, the background radiation has been referred to. These are experimental details. Why don't you elaborate?
Well, I want to start by looking back. When I was a grad student, I wanted to be a particle theorist. And I showed up into Paul Steinhardt's office, who was mentioned in the preview here, and I thought he was a particle theorist. And he said, well, actually, I'm doing cosmology now. And I had this old school training in cosmology where there were big questions, no good theories, and no good data. And my heart sank when
And they were ministers who did that.
And then,
right.
And fortunately, Paul knew about the pioneering work that Alan had done, and also Andre was bringing particle physics to the universe. And so what's happened since then, I think, is one of the most triumphant transformations of a field in science ever, from having almost nothing to having just an abundance of riches that we've already been talking about. We've had, so the Planck satellite is the third in a series of radio telescope satellites that have given us successively better resolved, beautiful images way back into the universe. And just to give you a feeling of this Big Bang that we've been talking about, a good way to measure the time back is in terms of the density, which is ever higher as we go back into the universe. And so the density
What we're seeing here is the satellite itself, right?
And that's the satellite itself.
Talk us through these.
The satellite was launched a few years ago, and as we were going about our lives, it was busy in space, sweeping out, measuring deep into the universe. And we all agree that what it's looking at is the universe when the density was 100 million times greater than it is today. Today it's about 1 atom per cubic meter. 100 million times greater is what is creating that image. We're looking back in time to a time when the universe was that much more dense.
And this is a Planck satellite image?
And that's an image. So when Alan said that the little variations are from the quantum fluctuations, the great thing about that is that's just not hand-waving. There's an absolutely concrete mathematical theory where you put in the quantum field theory, you put in the gravity, you turn the crank, and you get an answer for what you're going to see in an image like that. And I think it's unusual in science to have such a concrete mechanism. Every step of the way, these guys know how to do it, and they turn the crank and produce theoretical predictions to compare with this data set.
Now, if I wasn't at the World Science Festival and I came upon this image, forgive me, I might not say, aha, it's the beginning of our universe. I wouldn't necessarily immediately recognize that as the beginning.
Yep.
What is it that's so exciting?
Been there 14 billion years ago,
yes, exactly.
okay?
What is it that's exciting about this image? Because either we're talking about the quantum variations that you mentioned at the very, very beginning,
Yep.
or are we talking about the quantum fluctuations during the inflationary period? Which is it?
Well, it's that it's quantum fluctuations from inflation, or maybe an alternative theory. But maybe the way to say it is that I think we'll all agree that all our different theories say that what we're seeing in that image is from physics that happened so long ago that the density was actually a Google times higher than what we have today. So we all agree that the right science is to reach way, way back in the history of the universe and look at amazing physics that's doing something completely different than we see around us today, and that's got to be what tells us what's there. And furthermore, we have actual theories. We can do those calculations, and we can get maps like that. So it's really, really tremendous.
And I think it is very exciting. But again, having a little difficulty interpreting that image, I mean, what is to say that thousands of years from now, people won't say, and they took this satellite, and it went out, and it spun around, and it took these pictures, and they thought they were looking at the beginning of the universe.
Yeah.
How ridiculous is that? How can you objectively say that that data is giving you, in other words, what is it about
let's take it in steps.
Yeah, do it.
So I'm going to start by remembering back to 1992 when the first of these satellites made its announcement. And there was something very special that we've almost forgotten. And I remember, for some reason, I couldn't make it to that conference. Neil was there, and he called me up. He was so excited, and he said, it's a thermal spectrum. And it starts with the thermality, that the temperatures we're observing are real temperatures and not distortion. So in physics, a temperature is all tied with equilibrium, and if something's out of equilibrium, the temperature will, the notion of temperature will kind of be flawed. And the notion of temperature in this map is perfect. It's the best picture of a thermal state we have with data, and it's a great and to achieve that thermality. So the competing ideas back then, there were still people who thought maybe the universe wasn't so hot and dense in the beginning, but they couldn't get that level of thermal behavior out of their alternative theory. So we build it up in steps.
Andre Linde, what excites you most about what the Planck satellite is doing, and how much does it reconcile with what theories that you've proposed would predict? And then we will introduce the multiverse idea.
Okay. Well, actually, when I'm looking at it, when I looked at this picture for the first time, and that was the Planck-produced picture, it was in my flight from Geneva to San Francisco, and I downloaded the papers just 10 minutes before the flight, all 30 of them, and I was looking at them, and I'm not that sentimental person. I was nearly crying, because it is just magnificent. What we see right now, this is a photograph. All this, the size of the sky, the biggest photograph ever. And then what it shows a photograph of quantum fluctuations, which were produced 10 to the minus 30, about this, seconds after the Big Bang, like 1 billionth of a billionth of a billionth of a second, produced. Then, according to this inflationary theory, they were stretched all across the universe, the exponentially large scale. And then they produced our galaxy where we live right now. And then we see them at these images. And then these features of these perturbations, they were predicted by inflationary theory, and then we're checking and we see exactly what was predicted there. So this is just a magnificent result, and we are all happy that we are living. I never believed that it's possible. When we invented inflationary theory, I knew theory must be right. I knew it will never be checked, because it's just impossible. It's technologically impossible. And then I learned how to respect our experimentalist colleagues. They are smart.
Yes, yeah, they're amazing.
But were you a little bit nervous when they said, actually, we're going to check it? We're going to check it. Did you get a little nervous?
Look, I remember somebody told me, I don't remember where it was, that Einstein, when he received the results confirming or not confirming general theory of relativity, he said that if there would be a non-confirmation, then it would be bad for experiment. So this was the feeling with which we were living, because I must explain why people were so excited about the inflationary theory. Einstein always wanted to find out one unique explanation of our universe, to explain why it is everywhere the same. He used something which was called cosmological principle. Cosmological principle means that the universe is everywhere the same, uniform, and that's why it is uniform, because of the cosmological principle. And a long time ago, I used to make a joke, because I did not know who invented this cosmological principle. I used to make a joke that some people do not have good ideas, but they have principles. And then I learned that actually Newton also used it. But nevertheless, what we wanted, not just to say, oh, this is a principle. Because if you say that the universe must be uniform, then where are the origins of the galaxies? So you cannot be considered a man of principle if you take small bribes. You cannot say that the universe must be uniform and here are the galaxies. So you noticeable things, right? So that's what inflation tried to do. First, explain why the universe is uniform. Second, explain what are the origin of these galaxies, all together in one package. And what it did, first, it rapid stretch of everything which was before. Think about Himalaya, and you stretch this Himalaya by the factor 10 to the degree 10, 10, whatever. Inflation does it so much that instead of Himalaya, you have a flat space. So nobody would go in, alpinist journey there, because it will be totally dull.
Easier to climb, though.
Oh.
Easier. Everyone in this room could climb.
Maybe with my knee, yeah, that would be a good idea to go there. But not interesting, no, probably. This was the first thing. So this is what inflation does, but then if simultaneously it will not reproduce galaxies, this would be a disastrous thing. So what we did, well, actually, our colleagues did, whatever. So what happened, come on. I was in Lebedev Physical Institute, and my colleague next door, Mukhanov, he was inventing at that time theory of quantum perturbations, which were expanding and producing galaxies during exponential expansion of the universe. And I said, what nonsense. Can you produce anything classical from anything quantum? Galaxies are huge. We're talking about quantum fluctuations. No. And then I understood that without this, I would not be brave enough to come with a continuation of Alan's theory of inflationary universe, because if inflation happens only to erase all structure which existed before and not produce anything instead, then it would be a disaster. You'll have all homogeneous universe, not one person there, not including me or us, whatever. So that is definitely contradict experimental data. So what we try to do something better than that. And yes, indeed, we are able to explain how galaxies are formed. Now, so what we did, we explained how the universe is homogeneous, and we then answered Einstein that we know how to explain the uniformity. Then we explained how on top of this homogeneity, we get some inhomogeneities, very important in our life. And then the next step, and that was something which was total surprise for me. When I was thinking about this universe expanding, like, look, think about the football, okay? So football have a black, white, white, and then a round ball. Now, think about it expanding this 10 to the degree 100 times, okay? This 10 to the degree 100, usually we write more zeros there, but it depends on the model. Now, so what happens then? Black territory becomes black and huge. So the person living on the block, he will look around and he will see, I'm in the black universe is everywhere black. Let me try to explain why universe must be black. okay? Because otherwise, these are my experimental data. But this is a part of the football. So another guy who is living on white, he will see himself surrounded by white, and he will be trying to explain why the universe must be white, because the only thing that he sees is white, and black is somewhere exponentially far away. He have no experimental idea what it is there. So now what we have right now is like what I call cosmopolitan perspective. Some live in black, some live in white, and that's just fine. Now, what inflation therefore does, it is first moment when you start thinking, actually, maybe Einstein wanted something more than we actually can give him, because he was trying to explain why the universe must be everywhere white. And then I see that in this simple picture is not necessarily. And then we start studying these quantum fluctuations, which are produced during inflation, produce these galaxies. And we have seen that in some parts of the universe, these quantum fluctuations tend to create another, again, new stage of exponential expansion, new inflationary universe. And then if this new inflationary universe can have different properties from ours, it may or may not ones, depending on the theory which we study. But if it can, then you have, even if you start with one white universe, it starts producing black universes. If you have many options, it will produce white, black, green, blue, whatever. And then we start thinking, okay, so how many different you may produce? And until approximately 2003, when I was working on it, and Alan was working, and Alex Vilenkin was working, and some other colleagues, when we were talking about it, other people say, nope. This is just nonsense, because who need it? We have one universe, one is enough, don't do it. And also...
Can I be one of those people just for a moment?
Yeah.
Who said don't do it?
For a moment, yes.
Yeah, for a moment. Let me just say for a moment. Can we put the Max Planck picture back up on the slide there just for a second?
And then I'd like to follow up
yeah,
on that as
absolutely.
well.
You can follow up. If we look at this picture that supposedly shows the picture of the universe very, very early on the Big Bang, what is it about that, or the mathematics, or the principles at work there that give you that picture, that make it so exciting, that suggest at the edge, you know, it's written in fine print, oh, by the way, continued in another universe? Why do you need to have more universes if this picture was so satisfying to you? Is it the math? What is it that implies there's multiverses? And then we'll get a follow-up.
Yeah. So first of all, the property of these perturbations which occur here, they have some interesting feature that the amplitude of the perturbations actually grows with large scale. So they are larger at larger scale. And then this suggests that if you continue going, that on some very, very large scale, it will be much larger than what we see here, and maybe of the order of 1. So it will be actually completely different from what we see. So this is just a hint. But what we have right now, you should think about it perhaps in slightly different terms. Previously, it was like that. Because this is what we see, and everywhere it is the same, then it must be the same for whatever reason. I don't know why, but it must be the same. What inflation say, that now that we have a possibility that the universe could have different properties, but they were just stretched, and we will have an illusion that they are the same, then the burden of proof that the universe is everywhere the same are on those who say so. Previously, it was like following from observational data. Now it doesn't. And then the next step which happened was most important in this, and it happened in the year 2003 when string theory entered the stage. So until this time, we did not know, string theory is king and queen of every possible theory of everything, maybe. Okay, maybe, but one way or another, this is the best that we have. So this theory, which is the best that we have, predicted that we must live in a 4-dimensional space, three dimensions of space and one time, but actually, fundamentally, our space has 10 dimensions. So 9 dimensions of space and 1 of time. And then the question, of course, we see only 3 of space. So how this happens that 6 others are not appearing? And then string theory said, okay, because these 6 others, they were squeezed into something tiny, tiny, which we do not see. And then we ask, so how can you prove that this is what is going to happen? And they say, we will prove next year. So, so they started doing it in '85, And until 2003, we did not know the answer. Then something else happened. We found that our universe at the present moment is expanding exponentially, slight, just a little bit, slowly. And then, well, Ed Witten, who is the god on string theory, have just mentioned in some conference in India that I would not know how to explain what? Oh, I thought that Ed is commenting.
Occasionally, the other universes protrude. Hold that thought for just a second. Let me get Andreas's follow-up.
So I actually think I had not meant to. This is a comment not for the wrestling phase, but I'll slip it in, even though I think we're entering that. The gold standard in science is actually ruling theories out. And one of the reasons these data are so amazing is that we have ruled theories out. So in the early days, we had very different competing theories. We had theories that these patterns that we see on these beautiful maps, maybe they would come from astrophysical explosions. That was a very popular idea at the time. We had ideas that those patterns could come from something called cosmic defects, and Neil and I both worked very hard on those theories. And those theories have just been totally ruled out by the beautiful data that we have. Mm-hmm. And that gives us a sense of real progress. And even though around the group we'd have different theories, our different favorite theories of what makes these patterns, they've all been narrowed down. So they all have a lot of similar properties, and they're all very different from the ones that failed. Mm. And so that's a real palpable sense of progress, that we're really narrowing things down in terms of what might be going on.
I'm thrilled that everyone's making progress and that people are working very, very hard. Let's just poll the stage here for a moment, because I think the reason why you guys came here is to find out if there's an actual perfect copy of you existing in another universe, much more successful than you are, and you'd love to be able to communicate with them and to find out what they did right and what you are doing wrong. That's certainly why I'm here. Who believes that there is absolutely a set, infinite or not, of parallel universes, and that's implied by the physics that we understand today? Raise your hand if you believe in the multiverse.
No.
Who does? Who believes?
I don't.
Multiverse?
Well, likely, I wouldn't say for sure.
Likely? Okay.
So,
and no. So we got.
no. So
it's 2 and 2.
Can I just comment?
Please go ahead.
As Andy and me were saying, the reason we both got excited about cosmology is we believe in theories that make predictions, and we wanted to test those predictions and hopefully prove some of the theories wrong. What's happened with inflation is because the mathematical underpinnings, in other words, the prequel to inflation, was never developed. Inflation never described what happened at the singularity, which preceded inflation. And so inflation has from the beginning been an incomplete theory in which this question of why the inflation started was never answered. So the question of the initial conditions before inflation is still a mystery, and in fact has become a bigger and bigger mystery over time.
Do you agree with that?
This in fact is the reason for the origin of the multiverse, that because inflation, unfortunately, is not a predictive paradigm.
So I'd take that a little further and say, so Alan's original paper excited us all by the promise it would explain the starting point of the Big Bang. And I think that agenda has yet to work. I think the explaining of the tuning that we perceive in our universe has not happened because it's gotten so messy. The prequel, the finite prequel, works great, and it makes these beautiful patterns. But then going to the prequel is where things get really messy. And I think everything depends on how that works.
How do you see the problem of what happened before the inflationary period, the prequel, and what's happening now?
Right. Well, I would say that inflation never from the beginning was intended as a theory of the absolute origin of the universe. Inflation is a theory of a certain stage of evolution of the universe, as was the Big Bang theory itself, as is biological evolution. So inflation was just one more step in our theories of evolution of everything. And none of our theories of evolution of anything go all the way back to the beginning. What we have found, though, and what I gather Andre will be talking about more in a few minutes, is that most models of inflation have the property that once inflation starts, it never stops. But instead, the inflationary region goes on producing what we call pocket universes, some of us call pocket universes, ad infinitum. And that makes the question of how it all started much less important. The question is still there and I think needs to be answered. And I agree it has not been answered yet.
But there's a very basic question in this picture of pocket universes, which is you cannot make predictions with it.
Well, that's
this
not
has
true.
become what's called the measure
Well,
problem.
let's get an understanding
Oh,
of
I'm
the
sorry.
pocket.
There is a major problem. I agree.
Yeah.
Let's get an understanding of whether the pocket universe idea is implied by some of the shortcomings that Neil has talked about regarding inflation, or if it's something that you conveniently need to pursue your own views of the universe. You've got some slides that help us to understand what these multiple universes look like.
Yeah, maybe they will show them, and I will be able to comment. So I actually can start with saying still what I started talking about string theory and why people actually start getting much more excited about the idea of the multiverse than they were 20 years ago. So what happened is that when string theorists try to address experimental fact that the universe right now is accelerating, they tried to do it and it did not work, tried to do it and didn't work. And you know that with string theory, it is very difficult to come to a real experimental test of it. And now here is a test. Here is experimental result and does not fit into string theory. So at this moment, string theorists start getting worried and they start working seriously, trying to understand whether it's possible to explain this accelerating universe. Now,
The experimental result you're talking about is the
Yes,
acceleration.
Yes,
The dark energy.
yes, acceleration. And that's what was done at Stanford, 2003. There was a group of people, Kachru, Kailash, the person from India, Trivedi, and I was like a cosmology consultant there. So we have found a way how to explain stability of these 6 extra dimensions in string theory, and simultaneously explain how the universe is accelerating in the context of this theory. Since that time, no gaps in this formulation was found so far. It is very difficult. String theory is extremely complicated theory. But what was found, instead of finding any contradictions into it, what was found that this squeezing of these 6 extra dimensions may come in many different versions. How many versions? Well, we suggested one possibility, and then people start counting how many others. Maybe if you will show the next one, it will be easy for me to explain what it is, and maybe we will return to this slide later. Is it possible to?
Yes, sure, here we go.
No, actually, even the next one. Can you? Yes, okay. So this is kind of image of what happens in string theory in these 6 dimensions. It's kind of image because this is 2-dimensional picture of 6-dimensional universe. So it's kind of cutting through it, right? But then what you see is that it is very topologically non-trivial. What I mean is that consider, well, you have a bowl and you take a hole and make a hole at it and you get this famous New York bagel, okay? Now you take a bagel and make a hole in it and you make another hole in it and make it like that, and okay, so you have all kind of things that you can do having a compact something, but maybe having lots of different holes and putting some different fields, etc. And depending on how you do it, you will later, as a result of that, have totally different physics in the remaining 3-dimensional world. So, how many different versions of it? And this is an estimate. So this is very conservative estimates. First, people made this estimate 10 to the degree 500 different possibilities. Then they start saying, actually, maybe it's 10 to the degree 1,500. Then they start saying, well, actually, maybe there's infinitely many versions. Then they return back. Some of the infinite actually happen to be not very good.
See, this kind of thing worries me.
Yeah.
You're not alone.
Oh, yeah, but the thing is that you need 1, 2, or 3 good ones. Okay, so we apparently live in a sufficiently good one, maybe not in the best. But what happens is that previously we thought that multiplicity is something in the mind of philosophers. You have just one universe, okay. So when I'm talking about this football analogy, why not white nevertheless? So what happens is that if you study string theory and you try to explain why universe is four-dimensional and why it is accelerating, it brings you this multiplicity of choices. And then anybody who says, now my theory, like Neil, for example, my theory is based on string theory. Come on, if you say these words, you are in the multiverse because you have these 10 to the 500 degrees states. And if you want to prove that you are not, then you must prove that you are working in a version of string theory where you can live in just one of these states and others don't exist. So at the moment, we do not have any versions of the string theory where this happens. So these explain you why we decided we took this thing.
Great. Let me just say, I'm going to let you right in. Let's just say my concern, my anxiety about an untestable theory, string theory, being used as proof of another untestable theory called the multiverse, that just as a debater worries me. How would you answer that, Neil?
I would answer it by saying that this claim that string theory predicts a multiverse of 10 to the 500 or more different possible universes is based on very strong approximations. It's very unproved. None of these universes which have been constructed, and they've only been partially constructed, there's no mathematical proof they make sense. None of these, well, I think that's very hard to disagree with.
But it is
but none of them is a dynamical universe. Each one of them, at the very least, has a singularity as bad as the Big Bang singularity we've always talked about, and none of these people who studied these universes has resolved that singularity. So none of them really makes mathematical sense.
Although the anxiety over what happened before the Big Bang sort of goes away if there's lots of universes being made, right? I mean, that's...
Well,
I don't think
less
so.
of a
No,
question.
I think before
you haven't dealt with the pressing problem, which is what happened at the singularity.
Okay.
And I'll pick up on that and just say that you have 10 to the 500 of something, but each one of these somethings is generating the multiverse on its own in this picture. And there's serious problems just with one of those multiverses. And having 10 to the 500, in my view, doesn't fix anything.
Right.
And the problems are that you can have infinitely many pocket universes. When you have infinitely many stuff, you can't even count them up, so you can't tell what you're predicting, which is more common than something else. And in particular, I feel a technical question of how you even do probabilities. So someone mentioned Las Vegas betting somewhere earlier in the evening.
It was a non-scientist who mentioned that earlier.
But I would say the way people use probabilities to cope with these multiple eternally inflating universes, you couldn't run a casino on that. They're not solid use of probabilities. Yeah. Everyone's still gripping, scrambling away, trying to get it to work, just for one. And having 10 to the 500 just makes it even more confusing.
Let me get a comment from Alan here.
Yeah, I think we probably should explain a little bit about this so-called measure problem, which Neil mentioned by name and Andreas mentioned by description. There is a measure problem, I think, in an eternally inflating universe, in a multiverse. The basic issue is that everything that can happen will happen an infinite number of times, which means that if you want to say that some type of event is more common than another type of event, it's hard to compare them if they're each happening an infinite number of times. So that is a problem which I have to agree is not a problem we have literally solved, but it is a problem we've made a lot of progress on. There are ways to regularize the counting, to decide what order to count things in. So for example, if we talk about the integers as an example of an infinite set, if you ask what fraction of them are even, if you put them in the normal order, half of them are even and half of them are odd. If you decide you can forget the order, you might realize that you can order the integers in a way that you can get any fraction you want. You could put the first two odd integers followed by the first even integer, followed by the next two odd integers, followed by the next even integer. And if you get my drift, you can arrange all of the integers, every integer appearing once, so that 2/3 of them look like they're odd. So you need a regularization procedure, some way of ordering the counting to make the probabilities unique. And people have been studying that now for 5, 10 years. We certainly have prescriptions that give reasonable answers. We don't yet know what determines the right prescription, so it is still, I think, an unsolved problem. But the fact, to me, the fact that it's an unsolved problem doesn't mean we have to abandon the field. We've always had unsolved problems in physics, and we go ahead and find ways to solve them. And I think that's the route we should be following here.
It does mean the theory isn't a predictive theory.
Well, it means the theory needs to be completed. That's right. It means the theory is not complete. I agree with that.
But isn't it the case that sometimes theories predict and sometimes theories are an attempt to resolve unresolvable issues that are contained within our incomplete understanding, right? And in some ways, a multiple universe is kind of like the reordering of the integers. Why do we have them this way? They could be any way. And then suddenly the theory is, why are you ordering them this way? And are you somehow biased by the fact that you've decided to order things in this way? And so there's somehow a bias to having a one universe that if you just abandon that for a moment, you could understand more. I guess from my standpoint, Dr. Linde, you went from a theory that you believed in the beginning would never be checkable and then was by the Planck satellite. On some level, it seems like you've chosen a theory that really can never be tested except in an alternative universe. Is that the case, or do you think there is a testable sort of scenario here, either in your lifetime or mine?
Well, let us nevertheless, first of all, understand what do we like to do. Like, for example, if it's very difficult to check every integer because there are infinite number, then let's stop checking, let's stop counting because we didn't learn the strange attitude. What we learned, we have a totally different possibility of the picture of the universe. And until this possibility is ruled out, you are living with it. And then if you want to rule it out, then you should find experimental evidence against this picture of multiverse, because it's not the picture of universe which is fundamental. It's picture of, like, how many people there. Why do you think that it's fundamental to have all these people being alike? That's absolutely ridiculous. Like, all these colors, everything is built because of the same electricity, chemistry, few simple rules. Then you have so many different colors. You want to try to predict a theory which says that everything must be red. I just happened to came from the country where everything was supposed to be red. And I was amazed when I came to this country and I found that they want the same. So that is just strange, because we really have this possibility to vote, you come there and there is one name there. So how do you choose? So having no choice, it's a very, very strange choice to make. Now, if you have a basic picture that you have multiverse, then you may try to find an experimental evidence saying that is universe. If you say that you cannot find experimental evidence in favor of universe, then you are the loser. But then there is something else to it. Sometimes this idea of the multiverse, and the reason why it was so greeted by string theory community, was that sometimes it allows you to address questions which are otherwise are not addressable. Or at least for many, many years we were trying to address them and we failed. And one of these reasons was why energy, it will look stupid, but this is one of the most complicated questions physics was trying to address. Why empty space doesn't have any energy? Because we do not see anything there, it's empty, why it is empty, whatever. So in quantum field theory, actually not only in this, but this empty space can have extremely large energy, which Einstein called cosmological constant. So why this cosmological constant is zero? We were trying to prove that it is zero. We failed. For many years we tried, and we failed once after another, and then suddenly cosmological observation said that it's actually not zero. It's tiny, 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 almost nothing. It is 120 orders of magnitude smaller than the natural prediction of string theory, of every other science. So you come with this ridiculously small number. And explaining zero could be some maybe cancellation, one another cancels, so this may be possible in principle later. We failed for 30 years, maybe we'll find out the solution later. But this is this 10 to the minus 120. The only explanation that we know right now is based on a string theory multiverse picture, because you have these 10 to the 500 different universes. In some of them, you have small value of vacuum energy. In those where vacuum energy is larger, you cannot live there because galaxies would be torn apart. In those where energy density is negative, those universes would collapse. So you can live only in those universes where you can live. If you have choice of just one, this would be a magic surprise. Why 10 to the minus 1?
All right. So you make a compelling argument, but you also betray the notion that if you grew up in the Soviet Union before 1989, the idea of an alternative universe would be peculiarly attractive to such an individual. So all right. Let's just mull that over for a moment. You have an infinity problem with the multiverse that I want to hear about, and you have an alternative set of theories that I want to hear about. Andreas, you go first.
So I will start by saying some of these issues I've mentioned, the probabilities, the counting, and Alan's elaborated on that. But I have to say that a lot of the differences amongst us have to do with how we read the clues about the unanswered questions. And are these unanswered questions about to be addressed in a way that doesn't really change much, or are they shouting out for a radical change? And I, for one, am very happy to see hints from other ideas, and also involving the dark energy that's come up a little bit, that there really might be a way to develop a truly finite theory and just let go of all these pocket universes and all the counting problems and probability problems we have. And the hints come from horizons. And if you, some of you have probably heard of black hole horizons, and there's a very interesting property that if you sit outside a black hole and watch something falling in, you will actually never see it cross the horizon. Now, with the dark energy that we've observed around us, there's another thing happening, which is a similar horizon is developing all around us, so that we will never see, about the size of the observed universe, that we would never see something exit that horizon. Now,
So the invisibility of things at the event horizon on a black hole is similar to the kinds of horizons that you envision for a finite
another
universe.
kind of event horizon, yes.
Right, okay.
And so what you can envision is a completion of that theory where there's very interesting physics happening on that horizon that actually seals it off. And that's the whole universe.
And is that a little bit of what this graphic was here? We can roll that again, and you could sort of talk us through it. No, it's all right. So, talk us through it.
So one of the interesting ideas associated with this idea is that the information and the physics needed to describe that universe is actually completely finite. There's a finite number of possible states for the universe. There's a finite maximum entropy. And most of the interesting information resides actually on that horizon. And in a way, the idea that there's a universe beyond there is an illusion that's created by the physics on this horizon, and it just seals us off very nicely. And in a universe like that, you don't have infinite pocket universes. You have a totally finite system. It's plenty big enough to describe everything we see. And the other thing...
But the physics of that event horizon is not worked out.
Right.
That's the speculative part.
So I think we all are... You could take each one of us, and we have the speculative part, and it's sort of which seems the most exciting as a possible way to resolve these questions. So I find a finite universe very exciting, although I have to say, having early in life thought very much along the lines of my colleagues on the right here, I found it actually claustrophobic to switch from the infinite universe to the finite one. But I'm glad I did.
This is beautiful.
It's a much more...
There's 12 steps. There's infinite universes.
It's working out well for me.
Alternative theories, Neil.
Right. So my reaction to the inflationary multiverse was to draw the conclusion that this line of research has come to an end. And it's not fruitful when you end up with a theory that's not predictive. When it comes to the Planck satellite, it was mentioned that this data is consistent with inflation. But the trouble is that there are so many models of inflation that actually you could adjust the models to fit almost anything. And so I felt that's very deeply dissatisfying. So my reaction to it was to think, well, if we do try to complete the story, to find the prequel to inflation or really explain the singularity, and if we do try to complete what is going to happen to the dark energy in the future, we might have a complete picture, and maybe it's much more predictive than inflation. And so I'm looking to use the failures of our current view of physics to guide us towards the future theory that will be complete. So maybe I can show you a picture, a movie of the scenario Paul Steinhardt and I imagined, which was inspired by string theory, mainly because that's the most complete mathematical framework we have, including gravity and quantum effects. And so if it begins with an empty, flat universe, in fact, two universes, which are parallel to each other and separated by an extra dimension of space, that extra dimension has been magnified here so you can see it, but actually it would be much smaller than the size of an atomic nucleus. The gap between these two three-dimensional worlds, pictured as two-dimensional sheets. So the history of the universe is as follows. We start with an empty universe full of vacuum energy. It's the vacuum energy that causes these two universes to pull together and collide. When they collide, that's the Big Bang. It fills these two universes with matter and radiation, and they form galaxies, and then the vacuum energy takes over, and the cycle repeats again and again. So this was our alternative to inflation we came up with. It's a cyclic universe scenario. We completed it in exactly the same detail that inflationary models are completed. We made predictions before the satellites measured the sky. They agree to exactly the same precision that the inflationary models agree. It's not a satisfying theory yet because it too is very arbitrary. We had to introduce various free parameters and functions and so on, which I'm dissatisfied with. But I think it's really good to have a rival theory, a different picture of the history of the universe that does not involve inflation. It doesn't involve the multiverse. And it involves, it is of a universe which determines its own state dynamically. So if you're trying to explain the vacuum energy, which, as Andre mentioned, is deeply puzzling, why is empty space full of vacuum energy whose value is so minuscule in the units we would expect it to be? It's 10 to the minus 120 in the units we would expect it to take. How can we explain that? One way is that the universe is just very, very old. It's been cycling and cycling and cycling for a long time. And during these cycles, the vacuum energy has gradually relaxed. And it turns out that the lowest possible positive value of vacuum energy is the one that lasts way the longest in such a universe. And we've shown that. So there is a possibility within this scenario of actually explaining the puzzling value of the dark energy that's measured.
All right, we're going to conclude here in the last few minutes and get some final thoughts and mix it up a little bit. Just call me a dim-witted one-universe guy, but I'm just wondering if there's really that much difference between a multiverse and the two universes colliding thing. I mean, once you get beyond one universe, you're already out there. So I'm just wondering, multiverse, that's ridiculous, but here's two colliding universes. That's not ridiculous. Help me out with that a little bit.
That's a very good point. And you see...
Well, they're infinitely large, too.
The picture, as I mentioned, this picture was inspired by string theory. If you ask me, do I honestly believe there are two universes? No, I don't. I believe this is a mathematical framework which points us to how we can describe the singularity itself in a way which does not involve infinities. Okay, so this is another infinity. The Big Bang singularity is when the density of matter in the universe was infinite. We need to get rid of that infinity in order to describe it. In this two-universe picture, when they collide, the density is finite. The Big Bang had a finite density in this model. That is a hint as to what kind of mathematics we need to describe the infinity. And it turns out that the Planck satellite and the Large Hadron Collider results are pointing towards the same kind of mathematical resolution of the Big Bang singularity. And that's what makes me very excited. I see a more compelling theory around the corner.
Rebuttal, final thoughts from you, Alan?
Okay. First of all, I point out that I think very few people interpret either the Planck data or the LHC data in the way that Neil is interpreting them. I certainly don't really know what he's talking about.
For me, that's true of all four of you.
Neil advertises his two universes clapping theory as a way of avoiding the infinities of the multiverse, but the multiverse has a measure problem because everything that can happen will happen an infinite number of times. And his infinitely cycling multiverse, two universes colliding, also has the property that everything that can happen will happen an infinite number of times. So as far as I'm concerned, the measure problem is just as real in his model as in eternal inflation. And it should be pointed out that in his model, as these branes are colliding, they're also exponentially expanding perpendicular to the
branes
well.
refers to the surfaces. They're called branes, membranes. Right. It's a use.
Good point.
Right? Okay, thank you.
So he again has an exponentially expanding infinite universe. Same thing, same problems. I don't see any resolution whatever or anything that points towards that scenario. If we look at what string theorists are telling us, as far as I can tell, almost every string theorist, there are some exceptions, but almost every string theorist believes there are many more states than the essentially one state that Neil would need for his simple model that goes on with two branes colliding and nothing else ever happening.
So string theorists say things and we respond to the strings. We call that puppetry in my universe. Maybe we should just stop listening to the string theorists, and you don't have to answer that, but your final thoughts, your rebuttal to what Alan was saying.
Let me share some final thoughts. So the sum total of all human knowledge is finite, and it always will be, even as we increase it. So really, our theories should be built in a finite way. Now, the concept of infinity can be useful in our mathematics, but it's only ever useful, it's only ever proven useful in cases where, well, it might be infinity, but maybe just very large and finite, and the math has to work pretty well for that to be useful at all. And so we've got finite data. We should have theories that don't depend on infinity. I think we need to have theories of the universe that work just fine for finite data, for finite ideas, and not depend on infinities to make the whole thing work. So that's my final thought. That finite is what we're made of. That finite is how language works, how programs work, how the practicalities of mathematics works. I mean, pi is an infinite number, but you can get a nice round wheel for your car using a finite value approximation to pi. If you need a little bit rounder, you can extend pi a little bit longer. But the finite works just fine, and we should follow that in our physics as well as our
But
life.
Isn't that also an argument that the infinity doesn't matter as much as we think? No matter how much anxiety we have, you can still go buy a perfectly good tire for your car?
Well, except that my colleagues, and we haven't done the technicalities, really depend on these infinities to make their theories work. And so in technical discussions with each, I don't know so much about Andre, but they really insist on the infinity being absolute in these theories, and that's where I think the problem.
Neil,
a big problem.
for you, a final thought, a rebuttal, and then I'll hear from Andre, and I have a couple of questions about how I would dress in an alternative universe before we go.
Yeah, I do think the lesson of the last 30 years is the universe has turned out to be stunningly simple. And I think the challenge for theorists like us is to come up with equally simple, clear, predictive theories which give compelling results. And that would be to continue the tradition of theoretical physics, which is as the one science that has managed to discover magically simple descriptions of nature. I think it's unfortunate that over the last 30 years there's been this proliferation of models. It's due to, I would say, a lowering of standards, where we accepted models as legitimate, which failed to explain the most significant mysteries about the universe.
Well, not to prejudge the outcome in any sense here, I do have to say that for me, as someone who's studied physics and math as a non-scientist for much of my adult life, there is this tension between the proliferation of incomprehensible models anxiety that you've talked about here, but there's also this sense of suspending a set of biases that we need simplicity, or we need a particular order, or we need things to proceed according to our notions of time, all kinds of things that are built-in biases that we have. And one of the things that's attractive to me about the multiverse theory, and I wonder if you'd take us out here, Andre, is the idea that if we put aside as many of our biases as we possibly can, some of these things seem more interesting and attractive. If I was in one universe, would I be able to detach myself and know about the other universe in any sense whatsoever, or are we imprisoned in our individual universes, and there may never be an Andre speaking to Andre from two different universes in the future?
Interesting thing that when I was taking a ride in a taxi to San Francisco airport, exactly the same question was asked to me by the taxi driver. And that was amazing. 40 minutes. He was asking me all kind of detailed questions about the multiverse and string theory and everything.
You may not be helping your case
no,
here.
But nevertheless, and in the end, he also started asking me, and I couldn't believe it. He started asking me, and how would you answer this question which Napoleon asked about the existence of God? And then he said, oh, now I will drive always you, because it was so interesting. What happens is that we are witnessing the change of our attitude of how science is going to be built. Some of the leaders of modern science, like Steven Weinberg, whom I immensely respect, he said that what is going on right now with the theory of multiverse in particular, what is going on resembles what happened with the creation of special theory of relativity. Because when we start asking questions in a completely different way, when we envision a picture of our world in completely different terms from what happens before, well, it is like devil is out of the bottle already. Or genie, you call it, out of the bottle. Yeah, whoever it is, it's very difficult to put it back. And now this is what you see. You yourself here is an experimental proof. There is some reason of interest in this. The number of people who study this alternative cosmology does not change in time. It is Neil Turok and Paul Steinhardt. The number of people who is interested in the multiverse, like 30 years ago, it was equally small. And then it started expanding exponentially. And starting from 2003, it just grows and grows. Now, however, if you Google at it...
Well, there were very few people getting tattoos back then, too, and now that's growing. I don't know if that says...
I must admit one thing, though,
publication.
because something is teaching us modesty, and that's just Googling trends, okay? So Googling trends on the universe and the multiverse, and I checked trends on the universe gradually grows down. But then some peaks. And I was so encouraged that probably it's Planck satellite. And I've seen this peak of the interest is Miss Universe from Brazil. But now the interest in the multiverse steadily grows. And you are the experimental
multiverse.
So, it's decided then. We will reconvene this discussion and reconvene the whole multiverse discussion next year in Brazil. I want to thank Andre Albrecht, Alan Guth, Neil Turok, and Andre Linde for a fascinating discussion. Thanks to all of you. I'm John Huckleberry. Thanks so much.